Hello everyone, welcome to Jason Tech. I'm Jason. The previous video has introduced Trident, the main chip of the leaf switch used in the data center server access scenarios. In this video, we will talk about the SPINE switch chip Tomahawk. My channel shares high-level tech topics related to data centers, talking you to improve your horizons and skills. Follow me, turn on the little bell, and don't miss any high-level videos. In the early years, the data center network was a multi-partition structure. Each partition was a chassis-type core and access network, and the traffic model was mainly north to south. With the rise of the cloud computing, data center, big data, short videos, and other services, there are more and more horizontal large traffic and high concurrency data. If the traditional physical multi-partition architecture with the north to south traffic as the mainstay runs east-west traffic, the delay is caused by multiple hops. The problem of high traffic and bottlenecks is highlighted. Therefore, it's particularly important to break down the barriers between partitions and construct a data center dominated by east-west traffic. Therefore, this kind of data center model of IP cloud network constructed by leaf full uplink has appeared, that is SPINE and leaf. Traditional SPINE nodes generally require high-density 100 gig capabilities to connect more leaves. Before Tomahawk, this high density for the 100 gig capability, a high-density modular switch could only be built with chips. For example, with 256 100 gig interfaces. However, with the update and iteration of the component capabilities, Broadcom has launched a chip dedicated to fast transfer Tomahawk. The latest single chip, such as TH4, can achieve 25.6T bps. That is, a single chip can produce 255 100 gig interfaces. One box can carry 256 pieces of 100 gig. This is equivalent to inserting 8 36-port 100 gig boards into a chassis-type core of a data center. As you can see, it not only saves costs, but also saves energy consumption. At the same time, it avoids complicated coordination protocol caused by stacking dozens of chips, such as the high-G protocol provided by Broadcom. There are pitfalls in non-standard protocols. For example, sometimes the chassis-type core engine is switched abnormally. The core is restarted abnormally after the board inserted. And even cross-board forwarding passes through the switching network board. Inexplicable packet loss caused by abnormal pins of high-speed connectors, and forwarding black holes caused by these problems. For details, the standard SNMP protocol cannot be monitored. Therefore, multi-chips are fused into one chip, and multiple boxes are designed, such as 4 or 8, to increase architecture redundancy. At the same time, IP cloud networking is more standard through standard OSPF or eBGP protocol, plus ECMP multi-pathing. More generally, SNMP can be seen. I remember chatting with a customer of a car company before. The car company has sensors that send back data every 10 minutes and disperse the data to the distributed storage in the data center. At the same time, the returned data would be processed automatically. Large-scale horizontal concurrent traffic flows through the core. The core is chassis rich, and the business department will give slow feedback and abnormalities at every turn. He looked back at the network management software and found that SMB checks every 5 minutes, but the calculation is every 10 seconds, which cannot be monitored by SNMP. He plans to use gRPC to improve the accuracy of monitoring to second-level monitoring. I analyzed the problem with him. Second-level monitoring can improve the accuracy of monitoring so that you can see it, but it may not solve the problem. It is likely that packet loss happens on the core cross-card forwarding or multi-chip cooperative caused packet loss, or even the high-G protocol and other issues. To solve this problem from the root cause, it's best to upgrade from the perspective of manufacturer equipment reliability to the perspective of architecture reliability. Combining the single-chip, multi-courses, standard protocols, and redundant architecture I mentioned earlier to better improve the business experiences and solve the problem from the root. Another value is the delay. The chassis type cross-card forwarding delay will be relatively high because it passes through multi-chips. Currently, the delay of forwarding from a port of 100 gig cards to a port of another 100 card is about 5 microseconds. Well, a box-type devices with the same density, because it's a single chip, the forwarding delay of the 100 gig interfaces is about 2 microseconds. That is, the horizontal flow of the entire network. The processing delay of each flow can be saved by 3 microseconds. The delay of the entire network is reduced by 60%, so that the chassis type devices have no advantages. If it is traditional batch or transaction traffic, the traditional core and access network is held, which is more suitable for chassis-based networking because the manufacturer shields the complexity through chassis-based networking, and the networking is simple and convenient. Having said so much, let's take a quick look at the model, bandwidth, and features of this super-fast Tomahawk chip. The standard SPINE+LEAF architecture model and the spine position are usually used in the Tomahawk series chips in the Broadcom Strata XGS category. The chips have had 4 generations so far. The model number is also very easy to remember. The one starting with 569 is the Tomahawk series. Add 10 from the earliest BCM 56960 to BCM 56990. Then let's take a look at the first generation of Tomahawk 56960. Single chip 3.2T, suitable for 32-port 100 gig products. Suitable for small-scale spans, which are rarely used at present. Many extreme features such as VS-Line INT. The port density of the second generation Tomahawk has doubled, with a single chip of 6.4 Tbps, which can support 64 100 gig interfaces. The main features are these TCP and mode, that is, the chip's packet loss virtualization related functions. By the third generation of Tomahawk, it is the SPINE chip that is currently used more. The mainstream model is 128 100 gig ports. Now, the leading internet companies have used 25.6T TH4, that is, can provide 128 200 gig interfaces or 64 ports of 400 gig interfaces. For these enterprises, Leaf's uplink not 40 gig, not 100 gig, but 200 gig and 400 gig, which greatly expands the horizontal rate. Generally, the networking scheme of this chip will cooperate with the corresponding algebraic chip scheme for joint networking, usually becoming the third generation main chip solution, TD3 plus TH3, and the fourth generation main chip solution, TD4 plus TH4. I won't go into too much detail about the network architecture of the main chipset here. Later, I will release a series of videos to talk about the network architecture of the main chipset with you. Well, that's it for today's video. Let's leave a segment to see how well you have mastered it. How would you briefly describe Broadcom's Tomahawk series chips? The first dimension is why Tomahawk needed. Compared with the chassis type multi-chip architecture, what are the advantages of the single-chip architecture? In the second dimension, what models does TH have? I will put the answer in the introduction. Please leave a message if you have any questions. In the next video, we will focus on introducing the Generation Series chips. See you.